Usually, we think of distance as physical space, the miles between two cities or the inches on a ruler. But in mathematics, distance is a flexible concept. If you change the rules of how you measure distance, you change the geometric properties of the space itself. To understand functional analysis, we have to move past standard calculus. Instead of working strictly on the familiar real number line, we expand into a general abstract boundary. We call this undefined space simply set X. A metric space is defined as a pair, the set X and a metric D. Any two elements inside this set, let's call them X and Y, can be assigned a distance function, a strict rule telling us exactly how far apart they are. To qualify as a metric, this function must follow a few logical rules. First, distance is always 0 or positive. Second, the distance between X and Y is 0 if and only if X and Y are the exact same point. Third, the distance from X to Y is equal to the distance from Y to X. Finally, we have the fourth and most critical rule, the triangle inequality. If you add a third point, Z, the direct distance from X to Y is always less than or equal to the detour through Z. A straight line is always the shortest path. Stripping the concept of distance down to these four strict rules is highly practical. As long as your measurement follows these axioms, you can calculate the distance between scattered data points, complex infinite sequences, and even entire equations. On the Euclidean plane, distance between 2 points is a straight diagonal line via the Pythagorean theorem. But apply the taxicab metric to this same grid. Like navigating city blocks, you cannot walk diagonally. You calculate distance by moving strictly along grid lines. This grid-based math perfectly satisfies all four metric axioms. Because a circle is defined as the set of points at an equal distance from a center, the taxicab metric produces a shape that looks like a diamond. Since you can only move in steps, the points at one unit of distance connect into a square rotated 45 degrees. With the discrete metric, the distance between a point and itself is 0, but the distance to any other point is 1. Does the triangle inequality hold? The direct distance from X to Y is 1. The path through Z is 2. The axiom holds. A mathematical space is defined entirely by the ruler you choose to measure it. When you change the metric, you change the geometric rules of that space. Now we can leave physical grids behind. Consider a set made entirely of continuous functions on a closed interval. We write this space as CAB. This graph shows two continuous curves. To work in functional analysis, you have to stop seeing them as lines traced over an x-axis. We need to treat each entire function as a single, dimensionless point in a massive space. To do that, we need a metric. For continuous functions, we use the supremum metric. It scans for the widest vertical gap between the two curves across the given interval and logs that maximum value. That single maximum number is our distance. The complex curves collapse into single dots, separated by exactly that one value. We apply this exact same logic to infinitely long sequences. In spaces like L infinity for bounded sequences, or LP, the distance is calculated by comparing the differences between their individual terms, collapsing infinite strings of numbers into single geometric coordinates. Verifying these rules isn't always trivial. Proving the triangle inequality for advanced sequence spaces like LP requires heavy analytical tools like the Minkowski inequality, which we will tackle in a future session. By treating highly complex functions and infinite sequences as simple geometric points, mathematicians can use basic distance principles to solve difficult differential and integral equations. This diagram maps out the structure we've built. A metric space is simply a set paired with a ruler. The set can be anything from standard vectors to infinite sequences to continuous functions. Regardless of what you are measuring, the choice of metric dictates the shape, the bounds, and the rules of that space. Subscribe to the channel for more step-by-step breakdowns from texts like Rudin and Kreyszig, and to prepare for the IIT JAM and CSIR NET exams. Mastering metric spaces is the required first step. From here, we can build Banach spaces, study linear operators, and lay the mathematical foundation for